There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe. While many think it's just a comet, some theorizing a possible alien origin due to a few curious characteristics.
On July 1st, 2025, astronomers using the Asteroid Terrestrial-impact Last Alert System, or ATLAS survey in Hawaii, detected a faint moving point of light. This was the 3I ATLAS, the third interstellar object ever observed passing through our solar system. Unlike comets and asteroids, native to the Sun's gravitational reach, this traveler comes from beyond.
Now, astronomers have captured that moment live, streaming in real time around the globe of them watching all of this. Take a look at this.
Quantum AI has analyzed NASA's new 3I ATLAS images. What it found is terrifying. Today, we'll unveil what scientists have figured out so far. What makes 3I ATLAS unique? Officially designated as 3I, standing for Third Interstellar Object, this object follows in the path of one I, Oumuamua, which was detected in 2017, and 2I Borisov, observed in 2019. What makes 3I ATLAS unique is a combination of its extraordinary age, its unbound trajectory, its peculiar composition, and its relatively small but active structure. The most striking feature of 3I ATLAS is its estimated age, which ranges between 7 and 14 billion years. This figure places it at or beyond the age of the solar system, which formed about 4.6 billion years ago, and possibly even older than the Sun itself, which is around 4.57 billion years old. If these estimates are correct, the comet is a relic of the early Milky Way, formed during the epoch when the galaxy's thick disk was taking shape. The thick disk is an ancient component of the Milky Way, populated by old stars and stellar remnants that retain chemical signatures distinct from those in the thin disk where the Sun resides. That 3I ATLAS may have originated in this ancient structure means that it carries a chemical memory of an era long before Earth existed. Its mineral and molecular content may preserve conditions from the galaxy's formative years, when metallicity was low and primordial processes dominated. It is a time capsule from the deep past of the Milky Way, and maybe more. The comet's trajectory has also played a critical role in confirming its interstellar identity. Like 1I Oumuamua and 2I Borisov, 3I ATLAS follows a hyperbolic orbit, which means its path through space is not bound by the Sun's gravity. Its eccentricity, a measure of how open or stretched its orbit is, exceeds 1, confirming that it is not a returning body but a visitor passing through only once. Observations from ground-based telescopes and space-based instruments quickly established that it will never circle back. Data gathered by the James Webb Space Telescope, or JWST, in early August 2025, along with complementary observations from the Neil Gehrels Swift Observatory, revealed that the comet's coma is dominated by carbon dioxide. The relative abundance of carbon dioxide compared to water is among the highest ever recorded in a comet. In typical solar system comets, water is the dominant volatile component, with carbon dioxide and carbon monoxide playing secondary roles. In the case of 3I ATLAS, however, carbon dioxide emissions far outweigh the detected levels of water and carbon monoxide. These observations suggest that the comet formed in an environment where carbon dioxide was either more plentiful or more stable than water, which is inconsistent with the typical formation conditions of comets in the Kuiper belt or Oort cloud. This high carbon dioxide to water ratio could point to a birthplace in a region of its parent stellar system that was colder or chemically distinct from those that produced comets in our solar system. Another peculiarity lies in the comet's activity at great distances. Archival images from the Transiting Exoplanet Survey Satellite, or TESS, revealed that 3IATL-AS was already active in May and June 2025, when it was located approximately 6.4 astronomical units from the Sun, well beyond Jupiter's orbit. At that distance, most solar system comets remain inert, as solar radiation is too weak to sublimate water ice. Yet 3AC Atlas displayed a clear coma, indicating active sublimation of volatiles. This early activation underscores the importance of carbon dioxide, which sublimates at lower temperatures than water and can drive cometary activity much farther from the Sun. Follow-up observations with SWIFT in late July and early August 2025 also detected hydroxyl emissions near 3,085 angstroms, confirming the presence of water outgassing even at 3.5 astronomical units, where water sublimation is typically weak. This shows how different this comet is from solar system counterparts, and that its internal chemistry operates under a different balance of volatiles. In terms of its size and physical structure, 3IATL-AS appears to be relatively small. Based on photometric modeling and coma brightness, researchers estimate the diameter of its nucleus at less than 5.6 kilometers, with a more probable range under 3.5 kilometers. While modest compared to some of the largest comets in our solar system, its activity has created an extended coma dominated by carbon dioxide gas and dust, spreading tens of thousands of kilometers in space. Within this structure, the faint traces of water vapor and carbon monoxide can be detected, but they remain secondary to the overwhelming carbon dioxide signature. Moreover, the comet is entirely alien to our solar system, representing material that formed around another star billions of years ago. Unlike 2I Borisov, which resembled a solar system comet in many respects, or 1I Oumuamua, which puzzled astronomers with its unusual acceleration and shape, 3I Atlas confronts researchers with a mix of familiarity and strangeness. Its age means that it predates the solar system and even many of the stars in our galactic neighborhood. The chemical composition frozen inside it may carry signatures of processes that occurred before planets like Earth had even formed. For scientists, this is thrilling, but also humbling. Another unsettling aspect is the recognition that interstellar comets may be more common than previously thought. The discovery of 3 such objects in less than a decade suggests that countless others may pass through our solar system undetected, either because they are too faint or too fast-moving to spot. While 3IATL-AS itself poses no impact threat, the fact that interstellar objects of varying size traverse our neighborhood raises the question of whether larger bodies, potentially hazardous to planets, might one day cross paths with Earth. Some planetary defense researchers note that the hyperbolic velocities of such objects would make them extraordinarily difficult to intercept or deflect if they were on a collision course. The true significance of 3IATL-AS lies in its scientific value. Its study brings together NASA's flagship observatories, including JWST and SWIFT, alongside international facilities such as the Infrared Telescope Facility, or IRTF, in Hawaii. The comet also provides a natural experiment in astrochemistry, testing how volatile ices behave in conditions different from those of the early solar nebula. It also offers a comparison point for Oumuamua and Borisov, helping astronomers develop a more complete picture of the diversity of interstellar visitors. After all, there definitely is more from where that came. 3I Atlas is not alone. For centuries, astronomers have speculated about what might drift in the vast spaces between stars. Yet it was not until October 2017 that humanity encountered its first confirmed visitor from beyond, 1I Oumuamua, a mysterious object discovered by the Pan-STARRS survey in Hawaii. Just 2 years later, in August 2019, a second arrived, 2I Borisov, found by Crimean amateur astronomer Gennady Borisov. By July 1, 2025, the Asteroid Terrestrial-impact Last Alert system had revealed a third, 3I ATLAS, another hyperbolic traveler sweeping through our solar system before returning to interstellar space. The message is unmistakable. These objects are not isolated anomalies, but members of a galactic population of wanderers. For most of history, they passed unnoticed. Today, thanks to advances in technology and new theoretical perspectives, they have become central to debates about the origins of planetary systems, the distribution of life in the galaxy, and even the possibility of extraterrestrial technology. The sudden string of discoveries raises an obvious question. If interstellar objects have always been passing through, why did we not see them before 2017? The answer lies in the limits of earlier surveys. Most comets and asteroids are faint and move slowly relative to background stars, but interstellar objects are fainter still and move much faster, entering and exiting the solar system in months rather than years. Before the 2010s, sky surveys lacked the sensitivity, field of view, and computational power to notice such fleeting apparitions. The Pan-STARRS 1 telescope atop Haleakala, Maui, was a game-changer. Its 1.8-meter mirror and 1.4 gigapixel camera began operating in 2010, designed to scan the sky for potentially hazardous asteroids. Its automated system flagged a fast-moving, elongated object in October 2017 that could not be matched to any known solar system orbit. Follow-up analysis confirmed it was on a hyperbolic trajectory. This was 1I Oumuamua. The detection proved that such objects are not hypothetical but real, and moreover, that modern wide-field surveys could spot them. The discovery of 2I Borisov in 2019 reinforced the point. Unlike Oumuamua, which was only about 100 to 200 meters long and lacked a visible coma, Borisov was a classic comet in appearance, with a nucleus estimated at 1 kilometer and a dusty tail stretching thousands of kilometers. Its trajectory was unambiguously interstellar, and because it behaved like familiar comets, astronomers could apply established techniques to study it in detail. Telescopes across the world, including Hubble and ALMA, collected spectra showing high levels of carbon monoxide relative to water, suggesting it formed in an unusually cold environment. By the time 3I Atlas appeared in July 2025, the astronomical community was prepared. Atlas, operated by the University of Hawaii and funded by NASA's Planetary Defense Coordination Office, is designed to detect objects on Earth-threatening trajectories. With its pair of half-meter telescopes scanning the entire visible sky every 2 nights, Atlas spotted the faint object at a distance of over 6 astronomical units. This was farther out than Jupiter's orbit. Initial orbital solutions showed it was on a hyperbolic path, confirming it as the third interstellar visitor. Observations from NASA's JWST and Neil Gehrels Swift Observatory quickly followed, revealing a coma rich in carbon dioxide and relatively poor in water, unlike most solar system comets. Today, automated surveys, wide-field cameras, and AI-assisted detection pipelines have expanded our reach. The Vera C. Rubin Observatory, set to begin its 10-year legacy survey of space and time in 2026, is expected to revolutionize this further. Rubin's 8.4-meter mirror and 3.2 gigapixel camera will scan the entire southern sky every few nights, producing 20 terabytes of data daily. Astronomers estimate it could detect 1 new interstellar object per year. The scientific stakes are high. Each interstellar object carries material older than the Sun. Studying them offers a galactic sampling of planetary formation environments we cannot otherwise reach. Oumuamua challenged models with its cigar-like or pancake-like shape and unexplained acceleration. Borisov revealed a chemical composition unlike that of most solar system comets. Atlas has a carbon dioxide dominance and unusual activity at great distances. For astrobiology, the implications are profound. These objects could serve as delivery systems for water and organic molecules, seeding young worlds across the galaxy. The hypothesis that life's building blocks might spread via interstellar comets is already well established in scientific discourse. It is known as panspermia. In fact, many experts believe that life on our own planet may have originated through seeding via such objects. Conversely, they also pose a planetary defense concern. A sufficiently large interstellar object on a collision course could arrive with little warning, traveling faster than any local asteroid. That's how the dinosaurs, at least the non-avian ones, perished. But that's not all. In his 2021 book Extraterrestrial, Avi Loeb, a theoretical astrophysicist at Harvard University, argued that Oumuamua's anomalous acceleration could not be explained by outgassing or radiation pressure alone, and that it might have been an artificial probe or fragment of alien technology. Loeb has since expanded this work through the Galileo project, dedicated to searching for evidence of extraterrestrial technology in near-Earth space. Michio Kaku, a theoretical physicist and futurist, approaches the topic differently. In his public lectures and writings, Kaku stresses that the abundance of interstellar objects is a predictable outcome of planetary formation. Billions of icy planetesimals are likely scattered into interstellar space every time a planetary system forms, making the galaxy a vast junkyard of ancient debris. For Kaku, their detection reflects cosmic abundance. Countless systems like ours have flung their leftovers into the void, and we are only now developing the instruments to notice them. Mainstream astronomers take a cautious stance. Studies led by researchers such as Karen Meach from the University of Hawaii and Michelle Bannister from the University of Canterbury argue that natural explanations, though sometimes stretched, remain the most plausible. In Oumuamua's case, exotic outgassing of hydrogen ice or fractal dust could explain the acceleration without invoking aliens. In Borisov's case, the chemistry pointed to a natural but unusual environment of origin. With Atlas, the unusually high carbon dioxide content suggests formation far from a host star, possibly in the cold outer regions of a protoplanetary disk. With Rubin Observatory's LSST about to come online, the pace of discoveries is expected to increase dramatically. Each new visitor will provide chemical, structural, and dynamical data to refine models of how planetesimals form and evolve. If Loeb is right, one of them might even reveal technological signatures. If Kaku is right, we are simply beginning to glimpse the galactic ecosystem of debris. And it has always been there. In either case, the scientific payoff is immense. In the longer term, some propose missions to intercept future interstellar objects. The European Space Agency's Comet Interceptor, planned for launch in 2029, is designed to wait in space until a suitable target, possibly even an interstellar one, appears, at which point it will fly by and collect data. More ambitious concepts like Breakthrough Starshot envision ultra-fast probes propelled by light sails that could one day chase down interstellar comets for close-up study. For most of human history, the idea of an interstellar visitor was confined to speculation. In less than a decade, we have observed three. 3I Atlas is not alone. It belongs to a population that stretches across the galaxy, fragments of ancient worlds ejected into the void. Some may carry the chemistry of life, some may pose dangers, some may even hint at technologies beyond our own. Whether through the provocative lens of Avi Loeb, the cosmic ecology described by Michio Kaku, or the careful analyses of mainstream astronomers, the message is clear. Our solar system is not an isolated bubble but a crossroads in the Milky Way, where ancient travelers remind us of the galaxy's vastness and its enduring mysteries. But detection is only part of the process. Role of AI in current analysis. Modern sky surveys like ATLAS in Hawaii and the Transiting Exoplanet Survey Satellite, or TESS, launched by NASA in April 2018, produce immense datasets consisting of millions of images and light curves. Within these, the signals of moving objects must be separated from the overwhelming number of background stars. Machine learning algorithms are now routinely applied to automate this detection process, with systems trained to recognize faint streaks or changing positions that might indicate comets or asteroids. Beyond initial detection, spectral and image analysis of interstellar bodies has been transformed by AI-assisted pipelines. NASA's James Webb Space Telescope, operating since July 2022, and the Neil Gehrels Swift Observatory, which has been active since 2004, generate complex datasets filled with noise from cosmic rays, thermal fluctuations, and background sources. Advanced algorithms are used to clean this data and isolate meaningful signals. In the case of 3IATLAS, the identification of hydroxyl emission at 308 nanometers, a byproduct of water photodissociation, required careful filtering of background interference. AI pipelines sped up the process, ensuring astronomers could confirm water presence within weeks of observation rather than months. Modeling the orbit and activity of comets is another area where computational intelligence has become indispensable. The trajectory of 3IATLAS was calculated to be hyperbolic, ensuring that it is not gravitationally bound to the Sun and will eventually leave the solar system permanently. Standard orbital dynamics are relatively straightforward, but interstellar comets introduce complications when outgassing alters their path. As carbon dioxide and water are ejected, the resulting jets can nudge the nucleus slightly, creating non-gravitational accelerations. Machine learning models have been deployed to fit light curves and simulate coma expansion under varying outgassing scenarios. Similar approaches were applied to 2E Borisov in 2019, and to the still mysterious trajectory of 1I Oumuamua in 2017. While present-day AI tools have been highly effective, researchers are increasingly considering the potential of quantum artificial intelligence for astronomy. Quantum AI, which combines quantum computing with machine learning, promises to handle the massive, noisy, multi-wavelength datasets generated by telescopes far more efficiently than classical systems. An interstellar visitor like 3IATLAS produces overlapping streams of information. Infrared spectra from JWST, ultraviolet emissions from SWIFT, optical photometry from ATLAS, and potentially even radio observations from facilities like ALMA in Chile. Processing all of this together in search of subtle correlations, such as faint molecular absorption lines buried in noise, remains a major challenge for existing tools. Quantum machine learning could address this by analyzing datasets in higher dimensional space, identifying patterns that classical computers struggle to resolve. For interstellar comets, this might mean distinguishing extremely weak signatures of exotic molecules that would otherwise be lost. In the case of 3IATLAS, whose coma showed a carbon dioxide to water ratio significantly higher than solar system comets, quantum algorithms could provide more accurate chemical inventories. Quantum AI holds immense promise for the study of interstellar objects by improving trajectory modeling, which is complicated by gravitational interactions and irregular outgassing that often confound classical methods. With only 3 confirmed interstellar visitors so far, the dataset is limited but invaluable, and quantum-enhanced algorithms could accelerate comparisons of their chemical compositions and behaviors, revealing how galactic planetesimals differ across stellar systems. These findings matter because each visitor carries chemical signatures from environments that predate the Sun, offering insights into the galactic distribution of water and organics, the processes of planet formation, and the possibility of life's ingredients spreading between systems. While 3I Atlas itself is harmless, its presence underscores the open, dynamic nature of our solar neighborhood, and AI may be transformed by quantum methods into a tool capable of uncovering exotic chemistry and galactic patterns, turning what might seem terrifying into opportunities to study material billions of years old. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.